Okay, so let us continue. So before the break, so we looked at maximum a posteriori estimation, right? It's a map estimation, like where the idea is instead of just maximizing the likelihood, we were maximizing like the posterior of the theta distribution, which is in log space, it's just a sum of likelihood and prior distribution, right? Now, for the same coin toss example, so we also saw that the map estimator, in the end, is basically adding some numbers to the probability distribution, right? So now if you think about this 4 and 8, okay, now this just means that the other way to think about this is even before I started the experiment, in the imaginary world, I have done this experiment 8 times. Out of those 8 times, it is head 4 times and tail 4 times, right? So now at any point in this experiment, if I show you the fraction, you don't know what part of this fraction came from the prior and what part of the fraction actually came from the experiment, right? So in some sense, we can consider this as pseudo count. Okay, now these pseudo counts are imaginary trials that we have done so far, which gives us an idea of what should be the distribution. Okay, now if we go back to the same coin toss numerical example, right? So when you had n is equal to 20 and n1 is equal to 12 and n0 is equal to 8, right? So the MLE estimate was 12 by 20, right? So the map estimate, P map, is going to be 16 by 28, which is 0.571. So if I have to compare this with MLE, so PML was 0.6. So you can see that because of my prior belief that the p-value is going to be close to 0.5, like my posterior has been pulled to 0.571, from 0.6. Okay, it's pulled towards 0.5. Is that clear? Now, map is kind of generalization of MLE in the sense a map with uniform prior is actually equivalent to an MLE, right? So when you have a map with uniform distribution over all the theta values, then you don't have any preference over any particular theta. So then that is actually equivalent to maximum likelihood estimation. Is that clear? Any questions about map? Okay, so now we are going to look at our final estimator, okay, which is much more general than map. Okay, so we are going to do the complete Bayesian estimation. Okay, so in the case of map estimate, we were just trying to estimate one particular theta value, which is maximum a posteriori, right? Instead, in full Bayesian treatment, so what we are going to do is we are going to estimate a complete distribution over theta. Okay, so we are going to estimate the mean and variance of the posterior distribution and use that to actually compute the whole integral, instead of just approximating MLE or map. Is that clear? So we are going to use the complete Bayes rule without any approximation. So P of theta given x is given by P of x given theta, P of theta divided by P of x. Okay, where P of x is nothing but integral over all possible theta, P of x given theta, P of theta d theta. Right? So if I just integrate out the theta, I'm going to get P of x. Now, for MLE, we just cared about this. And for map, we just cared about this part, right? So we were cleverly avoiding this P of x so far, okay? So however, once you get into the full Bayesian treatment, like you have to compute this p of x. Now this p of x, which is this intricate integral, right? Like, so that is the most difficult part of Bayesian inference, okay? So in general, like Bayesian learning methods are not very superior to the frequentist approaches that we have seen so far in this course, mainly because of this reason, okay? It is just computationally very expensive. Like, so sometimes it is not even possible, like, because like the integral is intractable and so on, okay? So now, however, like we are going to make some restrictions so that we can still do this like in a much more compact way. So now the real inference process, right? Like, so if you remember, so this was given by theta, p of x given theta, p of theta given x d theta, right? So in the case of MLE, like I would just approximate this with, the given theta with theta MLE, right? Like in the case of map, I would approximate this with theta map. But in the case of full Bayesian treatment, like we're going to keep this as such, okay? And we're going to do integral theta over theta, p of x given theta, p of theta given x, sorry, I'll apply the base rule here. P of x given theta, p of theta divided by p of x d theta. Is that clear? So we will do this complete integral, okay? Now I told you it is very difficult to do, right? So, but let us try doing this for the coin toss example. So we're going to go back to the coin toss example. Okay, now let us compute the posterior exactly. Okay, so p of the parameter theta, which is p here, given c alpha and beta, is given by product over I is equal to 1 to capital N, p of c is equal to ci given p. So this is the likelihood part, right? Multiplied by the prior, which is p of p given alpha beta, divided by the evidence, which is integral over 0 to 1, product of I is equal to 1 to capital N, p of c is equal to ci given p, p of p given alpha beta dp. Okay, so all I have done here is like I have written down the base rule, but for the coin toss example. Okay, so this term that you are seeing here is the posterior. Okay, and this term that you are seeing here is the likelihood. This is your prior, and this is your evidence. Is that clear? So now, okay, copy the whole thing to the next page. Okay. So now we can actually substitute all the values and see what happens. So you have a product of the likelihoods. So it is p power n1, 1 minus p power n0. Okay. So then you have the prior distribution, which is the beta distribution. So it is 1 by b of alpha beta, p power alpha minus 1, 1 minus p power beta minus 1. Okay. Divided by, there is this very complex integral. Okay. If you think about what this integral is doing, it is really normalizing this probability distribution, right? So you have a probability distribution over p. The integral is just the normalization constant, right? So for now, let us just treat this constant as some z. Okay, let us not worry about how to compute it. Now, I can just restructure this. So I can write this as p power n1 plus alpha minus 1, 1 minus p power n0 plus beta minus 1 divided by b of alpha beta times z. Okay. Now, the numerator has a template, right? Like, so what kind of probability distribution would this be? So you have p power something, 1 minus p power something divided by some normalization constant. So what probability distribution is this? We have only seen 2 or 3 distributions today. So what distribution is this? Like, what distribution could be this? People can answer in the chat. Yes, I see answers in the chat. Okay, so what distributions we have seen so far? Bernoulli and beta. So does it look like Bernoulli or beta? Beta. It looks like a beta distribution, right? Like, because you have p power something, 1 minus p power something divided by a normalization constant. Okay. In fact, okay, so what do you need for this to become beta? So for this to become beta, you need something like this. Plus alpha minus 1, 1 minus p power n0 plus beta minus 1 divided by, you need b of n1 plus alpha, n0 plus beta, right? So if you have this particular normalization constant, then this is going to be equal, right? So now the interesting thing for this particular example is like this value that you see here, right? So this is actually same as this. Okay, now you can prove this by yourself. Okay, it just requires like a few more steps. Like you put the integral there, like you put the beta distribution, you bring things in out, you're going to get the beta distribution, this new beta distribution. Okay, now this means that my posterior is a beta of p given n1 plus alpha, n0 plus beta. Okay, now this means that every time you show me an experiment, I can integrate that experiment into my prior distribution, and I get a posterior distribution, which is also a beta distribution. Okay, now this posterior distribution has its own mean and variance, right? Like, so, like for example, like in the case of beta distribution, so the mean of beta distribution is given by alpha plus beta. Okay, and similarly, the variance of the beta distribution is given by alpha beta by alpha plus beta plus 1, alpha plus beta the whole square. Okay, now for our coin toss example, the mean is going to be n1 plus alpha divided by n1 plus n0 plus alpha plus beta, or in other words, n1 plus 5 divided by n plus 10. Okay, now you see that this is a little bit different from the map. So map gave you n1 plus 4 divided by n plus 8. Beta is giving you slightly different thing, and sorry, the like Bayesian estimation. But the advantage of Bayesian estimation is it is also giving you the variance. It gives you what could be the probability distribution. It also gives a variance over this mean, right? Like, so like you don't get that with map. So map is in some sense a point estimate. It just gives you the theta and that's it. It doesn't tell you anything about the distribution. So here you also get the variance. So the variance is going to be n1 plus 5, n0 plus 5 divided by n plus 11, n plus 10 the whole square. Okay, now let's go to the same number example like that we had, like n is equal to 20, n1 is equal to 12, n0 is equal to 8, right? So now the mean of this posterior is given by 17 by 30, which is 0.567. Okay, which is a little bit different from the map estimate. Now we also have the variance. So the variance here is given by 17 into 13 divided by 31 into 30 square. The numbers really doesn't matter. Okay, so this is just for you to go and see later. Okay, now let us try to, well, first of all, there is one mystery here. Like, so, like I told you that the normalization constant is very difficult to compute, but we have a nice way to do that here. Like, so I started with a beta prior. Magically, like I also got a beta posterior, right? Like, which means I don't need to do the integral. Like, so I can just do the computations without the costly integral, right? Like, so how did that happen? So we are going to talk about it. But before that, let us see a summary of all the 3 methods so far. Okay. Now, the green line that you are seeing here is the prior distribution over the p-value. Okay, so the prior actually peaks at 0.5. Okay, now you see an example. Like, let's say after this n is equal to 12 and n is equal to 8, right? Like you have seen 20 examples. Now, if you just go by pure likelihood, maximum likelihood approach, it is going to shift your mode to this 0.6. You see that the green line, like the green curve, has shifted to the red curve with the mean at 0.6. Okay. So, however, if you incorporate this prior knowledge and you do the posterior estimation, like map estimation, then you get this blue thing. Okay. And I think if you do the full Bayesian, like you get the blue line, which is the mean from the Bayesian estimation. Is that clear? So any questions so far? Okay. So now let's talk about the like one final thing, which is like, how did I arrive at a beta posterior, right? Now, for this particular example, the coin toss example, I actually picked the beta and Bernoulli distributions, like purposely, because they come from this nice family of distributions. We're doing Bayesian inference or Bayesian like estimation is tractable. Okay, so we're going to call this family of distributions as conjugate distributions. So if you take a conjugate prior, then you will always have easy way to compute the posterior. Okay, so what is a conjugate prior? So a conjugate prior, P of theta of a likelihood. Okay, so P of x given theta is a distribution, okay, that results in a posterior distribution. Let's just call it as P of theta given x, okay, with same functional form as the prior, okay, and parametrization that incorporates the data. Okay, so what is a conjugate prior? A conjugate prior is a prior which, when added to the corresponding likelihood, like when you multiply this prior with this likelihood, you're going to get a posterior which is coming from the same functional form as the prior. Now, this posterior is just going to integrate all the data from the experiments and come up with this new distribution. Is that clear? Now, as an example, beta is a conjugate prior for Bernoulli. Okay, so instead of picking beta for your prior distribution, had you picked any other distribution, then you cannot do this Bayesian estimation easily. Is that clear? Now, the biggest advantage of conjugate priors, like there are many advantages, like the first biggest advantage is determination of the normalization constant. 1 over z is simple. Like you don't need to do the manual calculation for the normalization constant. So like every time you do this conjugate like prior business, like so you will see that there is something in the numerator that is looking like the distribution. Then you can ignore the denominator and just assume that, okay, so this denominator is going to be this normalization constant. Okay. Now, the second advantage is you're going to have meaningful interpretation of hyperparameters. Okay. Like for example, like in the case of beta Bernoulli case, right? Like so, like we saw that the hyperparameters can be treated as pseudo counts. Right, like you can have meaningful interpretation for your like hyperparameters. Now the third advantage is it actually allows you to marginalize the likelihood parameters in closed form. Okay. So you can just use hyperparameters always, completely marginalizing out the likelihood parameters. Okay, we will see how to do that. Like, so for example, let us take the same beta Bernoulli case. Okay, so let us say we are interested in probability of C given alpha beta. Okay, now this is given by integral 0 to 1 probability of C given P, probability of P given alpha beta dp, right? So you're just integrating over all P, then you're going to get your evidence. Now, how would this look like? So this is going to be integral over 0 to 1 P power n1, 1 minus P power n0, 1 by beta of alpha beta, P power alpha minus 1, 1 minus P power beta minus 1 dp. Right? So now let me just write this in the next page. Now this is a very simple integral, as we will see in one step. So this can be written as 1 over beta function, like separated out, integral 0 to 1 P power n, 1 minus P power n0. Sorry, maybe I will just write it together. So it's going to be P power n1 plus alpha minus 1, 1 minus P power n0 plus beta minus 1. Now, can you tell me what is this integral? So this integral is the normalization constant for a beta function with n1 plus alpha and n0 plus beta, right? So we know that the normalization constant is another beta function. So this is basically beta of n1 plus alpha, n0 plus beta. Is that clear? So there are two beta functions here. Like I can just expand these beta functions if I want. So it becomes n1 plus alpha, n0 plus beta, okay, divided by n1 plus n0 plus alpha plus beta. And for the other one, like it's going to be alpha, beta, alpha plus beta. Okay. Now, so what have I done here? Like, so we are interested in computing probability of C given alpha beta. Okay. But you see that I have completely marginalized P. I don't see the parameter P anywhere in this equation. So this equation is just made up of n1, n0, which is from the data, and alphas and betas, which are my hyperparameter. Right? Now, this has a lot of advantages. Like, so what are the advantages? Like, so now you don't need to worry about computing the parameter. Like, so now you can start doing like sequential learning. Like, so like you see one example, you update your parameter config, like you update your model. Then you see the next example, you update your model. Now, updating your model to compute the posterior is really simple. Like all you have to do is just count n0 and n1 and substitute it here, like you have your answer, right? So computationally, it is very, very, very efficient when you have conjugate priors. Is that clear? Now, for example, like when you want to make prediction for the new example, given the data. Okay. Now this can be posed as probability of C is equal to 1 C given alpha beta given by probability of C given alpha beta. Right? Now I know how to do this. I know how to do this like by using the previous equation. So I don't need P at all. Like without using P, we can actually like easily integrate information. Is that clear? Okay, now it looks like conjugate distributions are like, or this idea of like having a conjugate prior has a lot of benefits, right? Like now there are a couple of questions here. So the first question is, do we have a conjugate prior for every possible probability distribution? Okay, so if we can have a conjugate prior for every distribution, then given a new problem, like let's say I'm modeling it with a particular likelihood distribution, then I can just pick the conjugate prior for that. Then I have a Bayesian approach, right? Like so, like which means that it's going to be always superior to maximum likelihood estimation. Okay. Now the interesting fact is you don't have conjugate prior for every possible distribution. Okay. There is, however, there is this one nice family of distributions for which conjugate priors exist. Okay. So this family is called exponential family. So exponential family is a special family of distributions with the property that conjugate prior exists for every member of this family. Okay. Now, again, most of the famous distributions that you have seen, like, or that we have seen so far in this course, right? Like, so they all actually belong to exponential family. In some sense, if something doesn't belong to exponential family, like it is very difficult to deal with. So probably we would not have used it. Okay, so like to give you some examples of conjugate priors, like when you have a Bernoulli data, the conjugate prior is beta. Okay, similarly, when you have a binomial distribution, the conjugate prior is again beta. Okay, when you have multinomial distribution, okay, then the conjugate prior for multinomial is given by Dirichlet. Okay, so Gaussian is always special. Like, so when you have a Gaussian distribution, can somebody guess the conjugate prior for Gaussian? The Gaussian itself. Okay, so well, I would encourage you to go read more about exponential family. Like, it actually has more distributions than what I listed here. But in general, like, you don't need to remember all these things. Like, so whenever you want to do a Bayesian approach for a particular problem, you'll first model the distribution. Like, then probably you'll go check if there is a conjugate prior. Most often we will make a Gaussian assumption, right? Like, so then you have the conjugate prior, which is Gaussian. And when you have discrete data, like most often you're going to make Bernoulli or binomial or multinomial assumptions. So this is actually a very good, like, popular set of distributions. Like, but there are also other distributions out there. Is that clear? Any questions about conjugate priors? Okay, well, so there is this whole community of researchers working on Bayesian learning. Okay, so in fact, it requires a different set of skills, in the sense you should be like very comfortable with these distributions, and like you should know exactly which distribution to use, like so that things are tractable and so on. Now, you can also go hierarchical here. Like, so for example, you can have a hyperparameter. Okay, so you have a probability distribution over your parameter P, okay, which is your prior distribution. Okay, now there's nothing stopping you from having a prior for the prior distribution. So you can do all those meta, like, and deep stuff even in Bayesian approaches. Okay, now to summarize, okay, so Bayesian learning, like, so why do we need to do Bayesian? Well, first of all, MLE can have very large variance, okay, and hence it leads to overfitting. Now, like, going Bayesian helps you avoid this. Now, the second advantage is Bayesian approach also gives you an estimate of uncertainty. Okay, so for example, like we saw in the coin toss example, that like the Bayesian estimate was not just giving you the mean, it was also giving you the variance, right? Now, this is actually important for several, like, sensitive applications. Like, so for example, let's say you are working on a problem which has a huge cost in making mistakes. Like so, medical applications are a good example. Okay, so now you want to do a treatment for a patient, and this treatment was suggested by the algorithm. The doctor would definitely like to know what is the confidence that this algorithm has on making this prediction, right? Like so, it doesn't matter whether the algorithm says like you have to take treatment 1 or treatment 2. Like it is more important that we know that the algorithm says you should take treatment 1 with confidence 0.9. Okay, if the confidence for treatment 1 is just 0.51, now if you don't know what the confidence is, like you would just think, oh, okay, so the maximum probability is given to treatment 1, I should do treatment 1. Maybe that's a mistake, right? So it's like these kind of medical applications or any financial application. Like, so let's say you are trying to come up with an algorithm for like stock investments. Okay. Now, whenever your algorithm gives you a strategic decision, you want to know how confident is your algorithm. Like, if the algorithm is not confident enough, then probably you don't want to take the decision, right? Like, so if you have access to uncertainty of the algorithm, then you can actually use this uncertainty to do post-processing. Like you can, for example, ignore the model's prediction if the uncertainty is too much. Or you can fall back to a human opinion, like if the uncertainty is too much and so on. Is that clear? Now, these are advantages, okay? But the disadvantage is, well, I should not put it in Y Bayesian, but the disadvantage is like, it works well with small data sets, but scaling it up to larger data set, like just like how we can easily scale up neural networks is very difficult. Okay. So now one can also have a Bayesian interpretation of neural networks. Like so the theta, the parameters in your neural network, if it comes from a probability distribution, then you have Bayesian neural network. Okay. So, but again, you have the same issues, like the computational complexity of training Bayesian networks, like Bayesian neural networks is much more complex. Okay. And one of the advantages of Bayesian methods is like you can actually use the prior knowledge in principled fashion. Okay. However, there is also a big catch with doing things like this. If your prior is a wrong prior, then your posterior can be very much off from the true distribution. Okay. So not also if your prior doesn't support your true distribution, then even if I give you infinite amount of data, like you cannot find the true distribution. Okay, so this is one reason why people normally tend to go for very generic priors, like which has a huge, like which has maximum support, and also like not very strong opinions about about the distribution. Is that clear? Any questions so far? Okay, so well, I know we're taking off breaks today. Like we are going to okay, so let's actually take a 10-minute break because I don't want to start fresh. Like so, we are going to see like a detailed example for doing Bayesian learning, but by using linear regression. Okay, so we're going to see how to do Bayesian linear regression. But I don't want to break the flow, so we will stop here and continue at 3:35 or 3:36.